Hello everyone and welcome to my Physics 201 Exam 1 review session. We're going to be going over a ton of concepts today ranging from kinematics to motion to acceleration to forces, even covering things like angular velocity, which is on some people's tests and not others. So I tried to make everyone happy for this exam review. This is the first time ever where it's literally two different exams, so I wasn't prepared for that. But the next time we have an exam review, like for exam 2, I'm either going to be putting together two different exam reviews, like one for each class, or like it depends how many students I have. I don't know what the breakdown is. If like all of my students except for one are in like the one class, then I'll just do the exam review for that one. So after this is over, just I'll probably ask or email what professor you have. So just wait for an email about that. I'm going to basically take a poll. But at least for now, we're going to be going over exam 1. 90% of the concepts are the same between both of your classes, so that's good. And you don't need a calculator today. I already did all the calculations ahead of time. And if you have any questions, or if you think I'm going too fast or too slow, or you need me to wait so you can write something down, please let me know. Just call out, unmute yourself. I'm not going to be checking the chat once we get started, so don't post in the chat. And finally, last thing is you see that I'm sporting you can't see it if you're watching the video, but I'm wearing a Dan the Tutor t-shirt. And the reason why I'm showing that to all of you is not just because it's cool, but also because if you get an A in this class, then you get a free Dan the Tutor t-shirt. So, yes, very exciting. Also, one more thing I forgot to mention, this is relatively important. The next time I do an exam review, that one will be not free. I do the first one free because, it's a business model, I suppose. But also because I'm going to give you a ton of value out of this. I mean, however much I charge, which won't even be... It's funny, whenever I do these exam review sessions and I charge my students, like these exam review sessions, I don't even charge as much as 1 hour, like for my private tutoring rate. And I give you like 3 hours worth of material, and like we have almost 30 questions to go over today. So it's a ton of value. So that's my little advertisement. Oh, and let's say you suck at physics, but you really want the Dan the Tutor t-shirt. I will gladly sell that to you for, I think it's like $25. I don't make any money off of it, but like it just covers the cost of making the shirt and shipping costs. So, with all of that being said, we're ready to get started. Not even number one. The first topic is dimensional analysis, aka converting units. What units do we like in this class? Typically we like meters, kilograms, and seconds for time. And there's going to be a couple more units we see later on, but these are the three big units: meters for distance, kilograms for mass, and seconds for time. I mean, we're not even going to see kilograms that much today until the end with forces. So in other words, when I have 10 kilometers per hour, and I want to know what that is in terms of meters per second, a lot of you know how to convert this very easily. Others of you don't. I don't care if you know how to or not. Here's what I do, and here's what I recommend you do. First, I write out 10 kilometers per hour, just like this. And then the first conversion factor is there is 1 kilometer in 1,000 meters. And notice the way I wrote that. I wrote kilometers in the denominator because the units cancel, and that leaves me with meters, which is what I wanted. Now I got to get rid of hours. And to do that, I know there's 1 hour in 60 minutes, and I put the hours in the numerator because, again, that cancels with hours in the denominator. So then if you think about it, what will the last one be from minutes to seconds? Well, of course, that's got to be minutes in the numerator and seconds in the denominator. And there are 60 seconds in 1 minute. And if you just multiply across, in other words, 10 and 1,000 are in the numerator, and 60 and the other 60 are in the denominator, you get 2.78 meters per second. And there's our answer. Any questions there? Okay, and then with that, we're going to move on. Next, probably the biggest math topic that will be on the first exam is trigonometry, sine, cosine, tangent, SOHCAHTOA. Highly recommend having these memorized. And just as a quick recap, I give an example here with this triangle, but sine is always the opposite over the hypotenuse. Cosine is always the adjacent over the hypotenuse. And tangent is always the opposite over the adjacent. And then as you can see, we have Pythagorean theorem here. Of course, that's important whenever we have vectors pointing at an angle. which then begs the question, what is a vector and what is a scalar? And for that, we turn to this right here. This little chart I have that explains the difference. So the biggest thing is that scalars have magnitude. That just means a number, like 5, 10, 12, whatever. And then vectors have a magnitude and a direction. And so some examples are 5 meters per second east, 3 kilometers, 30 degrees above the x-axis. Another thing you see I wrote is that speed is a... That's funny, that's wrong. Speed is a scalar. I need to fix that. Yeah, speed is a scalar, velocity is a vector. And one thing worth knowing is that speed, if I had to give it an equation for speed, I would just say it's the absolute value of velocity. So if you get a negative answer for velocity, just make it positive and you've got your speed. Also, whenever the question says magnitude, like they want the magnitude of the velocity, that means they don't want the direction. So if you get a negative answer, that means direction. Negative would be the negative direction. Just make it positive. So magnitude means make it positive. Magnitude equals positive answer. Okay. Any questions with that? And then the last thing I'll say is some common examples of vectors are the most important quantities in this class. In other words, velocity, acceleration, and forces, the most important topics on this first exam, are all vectors. And that means if it's a vector, you can add them together. But if you add vectors together, you got to be very, very careful. And that's what the next page is basically going to be about. So first we need to know how to add vectors graphically. When I say graphically, I just mean like on a picture. And to do that, all I got to do is connect the lines tip to tail. In other words, here's A, here's B, connecting them tip to tail. And then the answer is, what I like to do, I'll literally mark a start and an end point for where I started and where I ended, like Dora the Explorer. And then the answer is just the line connecting the start to the end, like that. So really it's just the red line is my answer. The black lines are just there for support to show you. And I wouldn't erase the other lines, I'd keep them, but I'd circle the red or at least just right off to the side like I just did. And then the other thing we can do is we can also subtract vectors. If you're subtracting vectors, then I don't like subtracting vectors, so I always like adding vectors. So if you want to add them, just add them, but you got to point it in the opposite direction. So instead of up and to the right, down to the left. And that's just as easy. So then that vector points to the right, then down and to the left points that way. And then again, I'm going to mark a start and an end. And then it points that way. Or in other words, just the red line. Down and to the right. Any questions on adding vectors with the graphs? Okay. So the next we're going to be adding vectors algebraically. That just means with numbers. Now, here's a question. Just tell me yes or no. Did you learn anything about x hat or y hat notation? In other words,
in lab,
you saw it in lab? Okay. So then, basically, and this is not a rhetorical question, this is actually a question for you guys. How do you add, like, vectors then? Like, if I have 5 to the right and 3 up, what would you call that? You know what I mean? Because we know we can't add them together, so what would you call that? Don't know?
I would do, like, x equals 5 and y equals 3.
Okay, I got you. So here's what I'm going to do today, because this is the notation I use. And since at least you saw it in the lab, I can explain it. X hat means right. Negative x hat means left. Y hat means up. And negative y hat means down. And even if like the hat's confusing, it makes it a unit vector and it's like a direction vector. But you don't even have to know what that means, honestly. It's not important. If you just want to say like 3x and 4y instead of the hat, I don't care. Whatever you feel comfortable with. I'm just telling you for today, since this is what I learned in both high school and college, this is what I'm going to be doing. And because it's honestly, it's the standard across the country for physics. Like, I don't know how you're supposed to do it without the x hat and y hat personally. But whatever. So if I want to add these two vectors together, notice they're both 5 long. I know one looks longer than the other, but they're both 5. Then all I got to do is only add the x's together and only add the y's together. So in other words, if this is 5 in the positive x, that's 5x hat. And this one's 4x hat plus 3y hat. Because it's 4x positive 3y. They're both positive. I don't have to worry about any negatives. And then if we want to add them together, then you would just say 9x hat plus 3y hat. And you can keep this as your answer if you want. It also depends if your professor or the test asks you for a magnitude. Like I said before, magnitude means positive, but it actually means something else too. If you ever see the word magnitude, it means they want you to, if you have x and y components, it means they want you to build a right triangle and solve the right triangle. Like the base is 9 because that's the x, and the y leg is 3 because that's the y. And then you're going to find theta and c, the hypotenuse, first using Pythagorean theorem to find c. So like c squared equals 9 squared plus 3 squared. And I'm assuming you know Pythagorean theorem, and you'll just get c equals 9.49. And that's one answer you could say. And then the other answer for the angle, what I would say is that tangent theta equals opposite over adjacent. So in other words, 3 over 9. So then in my calculator, I'd plug in inverse tangent of 3 over 9. Because if I want to solve for theta, the angle, it's inverse tangent. And then if you do that, you get theta equals 18.4 degrees. Any questions there? Anyone still writing? Okay.
I just have a quick question.
Go ahead.
So with tangent, do you, like when you do the inverse tangent, do you always do y over x?
Yes. Well, no, actually that's a good question. It depends. It's always opposite over adjacent, and most of the time it's y over x. But it's always opposite over adjacent. So then in the next 3 examples with these adding vectors, I want you to do these right now. I'll give you a minute. I want you to try these. And just go ahead. If you don't finish, that's fine. And time's up. So here's what you should have done. For the first one, an arrow pointing straight down, followed by an arrow that points up and to the left. And the result is start to end, so that red arrow, you should have an arrow that's basically mostly left and a little down. And as long as you have something close to that, I'm okay with that. Then for the next one, hopefully you realized it was minus, which means I'm really going to make it plus by flipping the direction. So then that would be down to the left, followed by up and to the left. And for that one, the arrow should just be straight, roughly straight to the left, like that. So straight to the left is our answer for the second one. And then the third one, probably the hardest, but first thing I do is I'm going to add it going the other way, like that. And if you add 3 vectors together, you just keep going. In other words, first vector points to the right, second vector points up, third vector points to the right. My answer cuts through it all and goes that way. So you got a big vector going up and to the right is our answer. Any questions? Okay. Next, number 2. Again, same thing. Try it on your own. We need to add these 2 vectors together, add the x and y hats together, and then I want you to find the hypotenuse using Pythagorean theorem, and I want you to find the angle using tangent. So go ahead. I'll give you another minute for that. Oh, and this you might actually need a calculator for. So if you don't have one, it's fine. Just let me do the math, and you can just have the work shown, and I'll give you the final answer. and times up. So hopefully, at least you recognize that I have to add the x's together, which 7 minus 2 is 5x hat, and then the y hat is just by itself, so I don't add anything. Now, the fact that you got two positive answers, positive x and positive y, means that this vector points up and right. The right because positive x hat, the up because positive y hat. By the way, even if you didn't know that, that's fine. That's like, just extra knowledge for you. But it means when I make my right triangle, it will be a triangle pointing up and right. If I did let's say I made a triangle going like down and left, that means it'd be negative x and negative y because that's down and left. And I would make the triangle look like that. But anyways, this is 5, this is 6, here's c. So hopefully you got c squared equals 25 plus 36. And if you actually solve for c with a calculator, you get 7.81. And there's c. And then again, if you want the angle, which would go right here, if you want that angle, then what I would say is tangent of theta equals 6 over 5, because it's opposite over adjacent, and theta would be the arctangent of 6 over 5, which as a number is 50.2 degrees. Any questions there? Okay, so the next example, this one is much harder. We're going to be doing this together. But I saw a question like this on the exam review that you guys had. At least I think so. You decide to walk to a friend's house who lives down the street. You walk 400 feet at 70 degrees north of west, then walk 300 feet at 20 degrees east of north. If you walk at a speed of... Actually, it's funny. The last part, like I ended up changing the question. I think this was too hard. So ignore this. And again, all I want to know is the displacement, which is our c in the Pythagorean theorem, and I want to know the angle. I don't care about the average velocity. We'll talk plenty about average velocity and average speed today. Don't worry. That'll just be later. So here's what I'm going to do first. I'm going to draw the picture of what's going on here. You may not also know what north of west means. When I say 70 degrees north of west, I'm saying north of west, here's my 70 degree angle. North of west. And if you didn't know that, well fine, then here it is. And that distance is 400. Okay. Here's my starting point, because I'm going north of west. And then from here, it says I'm going 300 feet, 20 degrees east of north. What's east of north? East of north is that way, with that being 20 degrees. And that's 300. And then somewhere over here is my end point. I don't know exactly where, but something like this. So then for this one, the secret is you got to break it up into two right triangles. Okay, we got to break up the 400 and the 300. And it doesn't matter what order we do that in. I'll do the 400 first. So let's say here's my right triangle with the 400. And again, here's my 70 degree angle. And I need my x and y components. Can someone tell me what the x component would be? Or which trig function I would use? It's going to be cosine, because cosine uses the adjacent. So then it's going to be cosine of 70 equals x over 400. And then x equals 400 cosine 70 degrees. And if you plug that in a calculator, you'll get 136.8. And that's positive. Well, actually, if we think about it, that's actually negative. Why is it negative? It's negative because which way does that angle point? It looks like it's pointing left, so it's got to be negative 136.8. Notice my calculator didn't tell me that. I had to figure it out, and that's fine. Sometimes we're going to do that. And that's the x hat direction, negative x hat direction. The negative sign you can either put in front of the x hat or you can put it in front of the whole number. I like putting it in front of the whole number because it reminds me I'm subtracting the number. And then the good news is, if I want to find sine, or the y direction, as soon as I say this, 400 cosine 70, I can immediately say this one has to be 400 sine 70. And remember what I said earlier, x is not always cosine, sine is not always y, but one thing's for sure, if one's cosine, then the other's sine automatically. So that'll save you like a minute, I guess. And so if you do that, y will equal 375.9. And can someone tell me that, if that will be positive or negative?
Positive.
Good, because it points up. So that's y hat. Okay, next I need the other triangle. For the other triangle, I see that it points 300 and up and to the right. So I'm going to draw that like this. Here's 300, here's y, here's x, and here's my 20-degree angle. Who can tell me, if I want to find x, how will I do it? I'm going to use sine this time. Why? Because sine is the opposite leg and x is opposite. So x over 300. And then just multiply both sides by 300. 300 sine 20. And I plug that in my calculator and I get 102.6. Is that positive or negative? Definitely positive because it points to the right. And again, if I want the y direction, then it's just going to be cosine automatically because we already used sine. So 300 cosine 20. And you plug that in a calculator and you'll get 281.9. Positive or negative?
Positive.
Positive again. And there we go. Now I have 4 answers. I'll box them so we can see them more clearly. I have 4 answers that I need to add together. And when I add them together, I can only add the x hats together and the y hats together. It's the whole reason why we've been, doing all this x and y stuff. So then what I'm saying is, for the x direction, it would be negative 136.8 plus 102.6. That gives me negative 34.2. And again, that's x hat. In other words, left, because it's negative. And then for the y, that's going to be 375.9 plus 281.9. And that gives me 657.8. And again, that's y hat, which means up. Any questions so far? And if I want the displacement, which displacement's just going to be the total distance, if I want the displacement, then I need to, again, to build a right triangle. A third right triangle for this problem. I know, I'm not even sure if you have room for that. Hopefully you do. But that means that it's going to look like this. Left and up. It was left negative 34.2. It was up 657.8. And then I have C, my hypotenuse, and some angle theta. And I want both. Now, by the way, when I do Pythagorean theorem and find the angle, one thing you'll notice is I'm actually going to make this positive 34.2. The reason why is because, as far as the math is concerned, for Pythagorean theorem, and I say c squared equals 657.8 squared plus negative 34.2 squared, when I square the number, it's going to be positive anyway, so I don't care. Like, you can keep it negative there, but it'll just be positive anyway. And I get 658.7, and that's my displacement after I solve Pythagorean theorem. And now for the angle, I'm definitely going to keep the angle positive. Why? First, let me write it. So if I do tangent theta correctly, it would be opposite over adjacent. 657.8 over... Again, I'm going to keep it positive just for a second, and I'll tell you why. Because if I solve this, I get theta equals 87.0 degrees. And I didn't actually do this, but if I quickly plug in 657.8 divided by negative 34.2, then I get an angle of negative 87 degrees. And now you're trying to say, well, what does that mean, negative 87? It has to do with like the quadrants and stuff. In other words, I don't recommend keeping the negative because it might just confuse you with your answer. Just make the components positive, and remember that this is 87 degrees north of west. Why is it north of west, you ask? Because here's theta, here's west, here's north, and we are 87 degrees north of west. And if you don't like that naming convention, that's fine. You can say up and to the left, I don't care. You can just draw the triangle, and you'll probably get full credit because the triangle is very clear too. But here's my angle. And are there any questions for that?
I just am still confused about the like north of west thing and like.
Then don't worry about
anytime.
it. I'm assuming, unless, is it in class? Is it in the homework or lab or anything?
I don't think so, but in lab we did like a vectors lab, and then if you got like a certain, it was like if both your components were negative, you had to add 180 to your final angle.
Okay, yes, that has to do with the quadrants and like the unit circle. Now, I'll be honest, like unit circle is like probably not going to be on this test, but it will show its face every once in a while in physics. And let me just show you how, just real quick, okay? Because here's the unit circle, here's 0 degrees, here's 90 degrees, here's 180 degrees, and here's 270 degrees. These 4 angles I would know. And if you get an answer, like let's say the answer's over here, right? And you get theta equals 40 degrees. Well, then that means it wasn't just 40. It means that just little slice of pie was 40. You'd have to add 180 to it to get the total angle. So like 180 plus 40.
So that would mean like in that quadrant, both of them are negative. So do you keep the negative signs when you do the tangent calculation or no?
Good question. Me personally, no, because I'm very good at the unit circle, and I already know if it's quadrant 3 because both x and y were negative. Then I'm just going to add 180 to it.
Okay, so you just like look at, that's just where I get confused because like in this, since we ignored the negative,
yes,
it would still just be 87 degrees. Like
yes. So remember, it depends what quadrant I'm in. In this case, I was in second quadrant, and if I get 87 degrees, which is this angle, then it's not 87 plus 180, it's 180 minus 87. In other words, 83.
Okay, so your final answer is actually 83.
Depends where I'm measuring, right? So if I'm measuring from like positive x-axis, like this angle in black, then yes, 83.
Okay, because that's like in my brain, that's how I think of it, is like.
And that's fine. You can do it that way.
Angle is.
Yep. And if you want to do it that way for like all the angles on this test, then I encourage you to. And if you're confused, then just like search a video on YouTube, like how to do unit circle, and another thing is it's called a reference angle. If you want to Google this when you're done and look up some videos on reference angles, the reference angle in this problem was the 87 degrees, and the actual angle is the 83.
So you just, instead of doing that, if you just ignore all of the negative
Also,
signs.
just real quick, I'm sorry because I'm terrible at math. It's not 83, it's 93. But you continue.
So if you ignore all of the negative signs, you just have to kind of think, like, where is my final vector pointing? And then from there, adjust your answer. Exactly.
And you should always know where your vector's pointing. Why? Because you need to know that, like, for instance, positive y hat, negative x hat, which is what we got, is left and up. Like, you need to know that at least.
Could you go over, like, on the picture, like, how you would draw the final vector, like, from the original picture?
Absolutely. I would, assuming that, like, it was something like this, and then the second vector was like this, okay? And I didn't know exactly where it went, because, again, this was a rough sketch, but it does mean that the final answer is up and left, which is, that's probably not enough of an angle. It's probably more like that, okay? I probably, like, messed up drawing the black one. It's probably more like this. But the red is my final answer. Does that answer your question?
Yeah, it would be, like, hard for me to tell that it's going up and left from, like, drawing the picture and then...
Yeah, so you don't have to tell from drawing the picture alone. Like, if anything, drawing the picture should be, like, a way to check your answer if it makes sense, not rely on it to get you the answer. And what I mean by that is that if you want the answer, look at the x
Oh,
hat and
I
y
see.
hat.
Okay, wait. Yeah, I see what you're saying. So like whatever the total x is and the total y, whatever the
Yes.
value, like okay.
Not the individual x's and y's. I don't care about that. When I add them together, that tells me the direction.
Okay. Thank you.
Yep. Any other questions? Okay. Then, with that, we're going to move on to probably our favorite topic, right? It's scaling. Yes, I know. We love scaling. So, we have I have 3 problems here on scaling. And honestly, it's probably not enough to fully understand scaling. But it's going to get you at least a start. And then you have to basically do the rest on your own with the tools that we're going to learn today. And places where I'd recommend looking for extra practice problems on scaling. Number 1, your lecture slides. There's a bunch of good questions there. And by good, I mean confusing and hard, which means good. And number 2, there was that practice test. There's a bunch of questions on scaling in that too. So the practice exam. And one more thing I want to say that's not related to this at all, but I forgot to mention, there will be a bathroom break at around like the 1.5 to 2 hour mark. So I'm just letting you know that ahead of time, so it's not a surprise. And if you have to go, then just wait, So, anyways, the strategy that I like to use for scaling is first think about the units. Think about the units. And the reason I say that is because there's 3 quantities we need to know. There's size, which can also mean length, and that's measured in meters. If I have an area, that's meters squared, and if I have a volume, that's meters cubed. By the way, it doesn't have to be meters always. It can be inches, it can be feet, it can be anything. The important thing is the squared and the cubed, okay? And so, in other words, if I want to go from size to volume, I got to cube my answer for meters. Or vice versa, if I want to go from volume to size, I got to take the cube root. And the cube root looks like this. Or if you want to, you can write it like this. 1/3 power. Means the same thing. But we're going to be doing more examples with this, so don't get hung up on this too much right now. Now, here's my 3-step process for the strategy. Step 1, convert both quantities to my size. Remember, size means length. It's not always length. Sometimes it's a width, sometimes it's a height, but length gets the job done, basically. And sometimes you can skip step 1 because sometimes it's already in size or length. And I'll explain what that means later too. Then step 2, you need to figure out change in original quantity. And what I mean by that is the question always sounds something along the lines of, if I change my volume and I double it, how does that change the specific metabolic rate? Or something like that. And what I'm saying is, if you change the original quantity, the volume, you doubled the volume, figure out what the change is. Again, go back to size. You got to figure out what the change in size is. Always go back to size. And then step 3, figure out change in second quantity. So in the fake example I just said, if the first quantity is volume, the second quantity is specific metabolic rate. And we'd use the conversion factor or the proportion to figure that out. And the more practice problems you do, the better you get at that. And one final note, and this is probably going to be the hardest part for you guys, or at least the hardest part for me to explain. There is an exception to the rule, and the exception is if you keep a dimension the same, and by a dimension I mean length, width, or height. If you keep one of those dimensions the same, cancel the units out. On the practice exam, this was like the cookie dough example. And you kept the height the same. And you'd have to cancel the height units out. And what does that mean? Well, I'll show you. But any questions before we do the first practice problem?
Go ahead. Sorry.
No, go ahead.
Do any of the practice problems include like stuff with logarithms? Because he also wanted us to do scaling with like power law and like.
We're gonna do that later, and
okay.
At least we're gonna do like the power, the exponent, and the none of that on basically the next page. And if you have any other specific questions after this, just email me or text me, and I'll answer your specific questions. So, anyways, we'll just go into the example. Number 4. If you triple the size of a cube, what is its change in volume? Okay, so step 1, I need to convert both quantities to size. In other words, what I'm starting with is literally the size. Okay, so the size is good. And then the other quantity was volume. We're eventually going to volume. And volume is really just a size cubed. Even though it's, like, technically that's only true for a cube, where the volume actually equals side cubed. But what I'm saying, the units of volume are meters cubed. And if I want to get back to size, then it's meters cubed. Okay? So what I'm saying is, size, we're good. I tripled, in other words, the original quantity, I'm good there. It's already size. Volume, I'm going to write it as size cubed. And now I'm going to say size is proportional to size cubed. Where did this proportional symbol come from? Honestly, just don't worry about it. What we're saying is, whatever I change to the size and how it affects my volume as the final answer, it's going to be whatever the change is cubed. And we'll see that in a second. But don't worry. We're going to get there. Step 2, figure out the change in the original quantity. This is very easy. I tripled the size of the cube, now it's 3s. Done. It's that easy because the original quantity was already size. So step 2 is easy. And then step 3, I need to figure out what the change is for my volume. Remember what we just said. Volume is size cubed. And we just tripled the volume. So 3s cubed. Like this. Notice I have to cube the whole thing. And hopefully you remember your properties of exponents. And if not, I'll tell you right now. This is 3 cubed times s cubed. 3 cubed is 27 s cubed. And remember, the s cubed just means our volume. So in other words, the answer is 27 times bigger. And hopefully that seemed simple enough where we have some momentum going into the next problem. But any questions on that one? Okay. Next for number 5. It's funny because a lot of times when we do multiple questions, I'll say, do the next one on your own. But these problems are so hard, you're just going to hurt yourself right now if you try it on your own. So I'm going to hold the handlebars. Number 5. If you double the surface area on an object, what is its change in surface area to volume ratio? So first I start with the surface area, I'll call it A. And I need to figure out how to convert both quantities back to size. So the first quantity's area, that's size squared. This is step 1. Area is size squared because area, of course, is meter squared. So it's got to be size squared. And then area to volume usually scares people until you realize it's just size squared over size cubed, right? Because A is size squared, V is size cubed. And you gotta know how to reduce these units. Size squared over size cubed cancels to just 1 over s. And so in other words, my relationship, instead of saying A is related to A over V, I don't care about that. I care that size squared is related, that's what proportional means. Proportional basically means related to 1 over s. So for instance, if just hypothetically, if I doubled my size and I want to find the change in this size, we can do that, and we're going to do it basically in 10 seconds. Okay, step 2, figure out the change in the original quantity. I want to double my area, 2a. Well, how does 2a relate to my size? Remember, a was s squared. So if I want to relate it back to size, then I am going to Watch this. We have an unknown variable here, x. Where did the x come from? I made it up. I put the x there because I want to figure out what my change in size is. X is the change in size. That makes logical sense. And again, our properties for exponents, if I square it, I'm squaring both the x and the s. And the s squared and the a are the same thing. Why are they the same thing? Because we said it right here. A and s squared are the same thing. So just cancel them out. 2 equals x squared. Take the square root. It's the square root of 2. You may be thinking, hey Dan, couldn't have I just taken the square root at the beginning and I get root 2a? And yes, if that's easier for you, then just take the square root that way and you get the same thing. I don't really care. But either way, the change in size is root 2. The change in size is root 2. Why is that important? Because now when I go to my final step and I got to convert this back to 1 over s, right? Then what I'm saying is the root 2 goes here, okay? It was root 2s, which means I just got to stick a root 2 in front of that s because the s's are the same. That's why we're relating them. So if you have root 2s on the left, that means you got root 2s on the right. And remember, originally it was 1 over s. Now we have 1 over root 2s. The change, what's the change? The change is 1 over root 2. The change is the difference. There's this root 2 that came out of nowhere. That's the difference. And if you plug that in a calculator, it's 0.71. 0.71 is my final answer, making the thing smaller. What was the thing? It's the surface area to volume ratio, which I don't even know what that means, but it's smaller by 0.71. Any questions there?
I'm just kind of confused with this step. Like,
which step? 1, 2, or 3?
3.
Yes.
Like, I'm just confused. So you have the like proportional thing of
yes.
s squared equals 1 over s.
Yes. You notice I'm not solving it.
it.
Like, if I were to solve it, I don't even know if I want to solve it because it'd probably be wrong. But I'm not like taking the square root. I'm not inverting this because this is 1 over. When I say like proportional, I'm just saying they're related. And related does not necessarily mean equal. What you should think of when you see the related or proportional symbol, whatever I change to this thing is the same change over here. And that's
so are you saying?
Yes.
This topic is just like so difficult for me to grasp. Are you saying root 2? Like, are you?
Here's what I'm saying. Forget about the squared. Forget about the fact that it's in the denominator. Just the s's. True or false, these s's are the same. And the answer is true. I'm not trying to trick you. The s's are the same because they're both size, whatever size means, length, width, height, whatever. And if you changed this to root 2, then because they're the same, you changed that to root 2 also.
So is it root 2s squared?
Are you saying for the left or the right?
For the left.
Yes, for the left it's root 2s squared. Do you know what happens when you get root 2s squared? You get 2s squared. In other words, 2a. We're back to the original. There's a lot of red lines and like connecting this stuff. All I'm saying is don't worry about, I think you're worrying too much about the math. And all I'm saying is the strategy to oversimplify it is to get it all in terms of s, the size. Because if you find one change in s, then you just found the other change in s automatically. And we got one more example. And you have like a ton of lecture sites to go through again and check. And you have like those practice problems on the exam too. And my videos. Like there's a lot more examples to do. And it's perfectly fine that it's confusing. Because believe me, I know it's confusing. But we just got to keep going through examples. Okay? Number 6. 2 cylindrical tubes of toothpaste have the same diameter but different lengths. If tube A has twice as much toothpaste as tube B, what is the ratio of the length of A to the length of B? This is the one that's kind of similar to that cookie dough example. And again, I'm relating two quantities. What am I relating? I'm relating not diameter, I'm actually relating volume. How do I know I'm relating volume? It's actually for the same reason as the cookie dough example, which at least I can give the same explanation. And that is, if you have twice as much toothpaste, the amount of toothpaste you have is a volume. It occupies a 3-dimensional space. So it's definitely a volume that we're saying is changing. And we're relating a volume V, we want to relate to a length L. Now the question is, what is the relationship? Well, to go to that, we need the volume of a cylinder, which I'm hoping they give you if you see a question like this. Although, I'm not sure if they would or not. Does anyone remember if they gave the equation for the cookie dough example? Because it's the same equation.
He gives us an equation sheet. I'm pretty sure it's on there, but I could be wrong.
Okay, let's assume it's on there just for this example, and you find it on the equation sheet. Here it is. Okay? Now, remember what I said. The exception is if something stays the same, the units cancel out. What that means is, even though volume I said earlier is size cubed, and this is kind of weird, on the right side you've got like a size squared times another size. Because radius squared is size squared, because you squared it, and height is just size on its own. In other words, this still makes sense because size cubed equals size cubed. Nothing too confusing there. But what I am saying is that because the diameter stayed the same, and diameter also means radius stayed the same, okay, because diameter is really radius, I'm saying cancel out these units. You got to cancel out a size squared out of this side. And what are you left with? You're left with size equals size. That's confusing, I know. But what that means is basically volume got to size S. Length was already size S. Size is proportional to size. So in other words, let's just say hypothetically I tripled the size, then I tripled the length. If I root 2'd the size, then I root 2'd the S, because they are the same. And what was the actual change in volume? The actual change in volume was twice, 2V. And because the units canceled, it's not cubed anymore. It's actually just 2S. I repeat, because the size, those dimensions canceled with the radius squared, you doubled the volume, you just doubled the size. Because it canceled. If it didn't cancel, just real quick, I'll show you what it looks like if it didn't cancel. Don't write this down, just observe, okay? But if it didn't cancel, 2V equals S cubed. Take the cube root of both sides. The change is cube root of 2. S. And then that's where I'd stick in on the other side of the equation, cube root of 2S. But again, it wasn't this because the units canceled. That's why this is a really hard example. But anyways, because it was 2S, I stick the 2 there. And so the answer is that it's going to be twice as long. 2 times as long. And so what's the ratio of A to B? I forget who's longer. A has twice as much as B. Okay, so ratio of A to B, 2 to 1. Or just 2. Hopefully it's maybe starting to make sense now. And again, if you want more examples, we have 3 more resources to do it. And again, we're just going to move on basically now because we just got to get through this. But honestly, the hardest part of the review is over. But are there any questions? Okay. Next, we're going to be talking about log scales. The second hardest thing for this exam, in my opinion. So, first we have the linear relationship. Linear is y equals mx plus b. And m is the slope, and b is the y-intercept, and we knew this since Algebra 1, so I'm not going to explain that anymore. That's very obvious. Exponential. First thing I need to say about exponential is that the variable, like x or whatever your variable is in the exponent. It's actually in the exponent. That's why they call it exponential. And what's famous for the exponential is that the y-axis gets the log. Now, it doesn't matter which log it gets. Could be log 10, natural log base 2, any log. But the y-axis gets the log. Only one of them. We call it a semilog. And then once you do that, after you take the log, then the slope is going to be your exponent. The slope is your exponent. And, one second. And the y-intercept is going to be the natural, or like the log of your number. Log of the, I'm going to say a constant a. What's a? Let me give you an example. If y if I have a function y equals a times e to the 5x, this is exponential. And the slope is 5. Slope equals 5. And the log of a, whatever that number is, could be 5, 10, whatever, log of a is the y-intercept. Any questions there? Oh, and by the way, this log has to match that base. Log must match the base. What does that mean? It means I can't just do any log. I have to do log base e, which is the natural log. That's the one I'm expecting to see on the test. It was on the practice test, and it's the most common example for exponential, is the natural log, ln. Any questions on exponential?
Could you go over that again? Because you cut out when you were saying it. Sorry.
No, that's fine. Thank you for telling me. What I just said was, and luckily the recording did not cut out, so we're going to be good there. But what I just said was the slope is 5 because that's the exponent, and because e is the base, your log must match the base. So then you can't just do any log. You have to do log base e, which is the natural log. So I did natural log of a, whatever a is. A could be 10, whatever. I don't know. Any questions there?
So the y-intercept is ln 2?
If...
Or, no, ln a, sorry.
Yeah, that's an a. That's a poorly drawn a. Because it's whatever the number is in front. And again, we're going to have some examples. But if I just literally put any number there for a, if I said y is 5e to the 10x, then ln 5 is my y-intercept. And what I'm also saying is, let's just say hypothetically I had y equals 20 times 10 to the x. Then my y-intercept is log base 10 of 20. Luckily, log base 10 is just the log button on your calculator by default. Does that make sense?
So whatever the exponent's attached to, whatever number that is log base, whatever that number is?
Yes. So like if this was 15 to the x, then it's log base 15 of 20. Yep. And then finally the power. So for the power, that's where I'm just going to erase some of this. I hope you don't mind because I'm running out of room. But for the power, both get log. Both the x and y axis get log. Could be any log again. Could be could be log base 10. Could be natural log. Could be anything. But let's just say I have y equals 20 times x squared. Notice x is in the base for the power. X is in the base for the power. In this example, the slope is always my exponent, so 2 in this example, and the y-intercept is always going to be whatever log you choose of the thing in front. Again, that can be any log. Unlike the exponential where they force you to use a log, you can use any log. Yeah, the exponential function forces you to use a log, like the natural log, for instance. But for the power, it can be any log you want. Log base 10 is the most common. Any questions there? Okay. Then for number 7, we're going to write the equation given the graph of the 3 examples here. And again, I'm going to help us through this. But first, I will ask you for some audience participation. For the first one, what is this? Is this exponential, power, or linear?
Power.
Yep, power, because it's both log. Can someone tell me the y-intercept? It's 2. The y-intercept is where it crosses the y-axis. It's with the starting point. And then can someone tell me the slope? So the slope is going to be rise over run. You can also do the y2 minus y1 over x2 minus x1 formula. But rise over run is easier. Rise over run just means how far up and how far to the right. In this case, 1 up, 3 to the right. So the slope is positive 1/3. And once we have these pieces, you know its power, you know its y-intercept, you know the slope, you have everything you need to build the power function. Y equals something in front of an x raised to the something power. We know the slope is the power, so we know the slope is the power is 1/3. And now the thing in front's the tough part. So you notice that I said log, right? I said log here, so that means log base 10. And normally what I do is, I'm just going to fill in a for now. It's a variable. We're going to solve for it, okay? Normally I say the y-intercept equals log of a. But now we got to do it backwards, right? Because we know the y-intercept's 2, and we don't know a. Does anyone know how to solve this? How to get rid of a log in math? You can't take the log of both sides because then the logs don't cancel. You have 2 logs now on the right. We don't want that. What we're going to do is the opposite of a logarithm. Yes, 10 raised to that power. So that means a equals 10 squared, which is 100. So the answer is 100x to the 1/3 power. And maybe that was a little confusing, but again, bunch of good questions on the practice exam you guys got and on lecture slides. And we got 2 more to do right now. So I'm going to erase this, assuming everyone's finished writing, just so I have room to write. Okay, so for the next one, again, I want to know first, is this exponential, power, or linear? It's exponential because only the y-axis got the log. How about what's the y-intercept? It's 6. Yep, thank you. And what's the slope? Count it out. What's the rise over the run? We're going down 1, 2, 3, to the right 2. That's the next actual coordinate point. Down 3, right 2. Down 3, right 2 is negative 3 over 2. So it's a negative slope. That makes sense. And since it's the natural log, you see natural log is on the y scale, we already know the formula is going to look something like this. Y equals some constant that I have to solve for, a, times e to the, whatever the slope is, so negative 3/2 x power. X shows up in the exponent this time. And the slope is negative 3/2. So the only thing we need left is the y-intercept. And again, we're basically going to do the same thing we just did, which is to say that the y-intercept is the natural log of a. And it's natural log this time because it said it in the actual graph. And we know the y-intercept. The y-intercept is 6, so 6 equals ln a. And if I want to solve for a, I want to get rid of the natural log. I take base e this time because natural log is base e. Last time it was 10. So the answer is a equals e to the 6, and you can plug that in your calculator if you want. You can also just literally leave it as e to the 6 power, and this is perfectly fine. E to the 6 is a really big number, that's why I don't care. But there's our equation. And by the way, as a fun fact, if you want to do these problems in reverse, in other words, you'll have the 3 answers written down, and then later on I ask you to graph them, then that'd be also a good challenge for you. If I give you the graph, can you graph it? If I give you the function, can you graph it? And you can do that after we're done today. And then the last one, I don't even have to clear space for. It's obviously linear, since it's the only one left, and more importantly, there's no logs anywhere. So someone just has to tell me the y-intercept and the slope, and we're basically done. Y-intercept is on 0 this time. What's the slope? Slope is 1/2. So then the equation is y equals 1/2 x plus 0. In other words, you don't even have to write plus 0. It's just 1/2 x. Done. Any questions there?
So just as like a strategy for these kinds of problems, should you just kind of memorize the different like the like standard form and then just try to like find all the missing pieces basically?
That's what I do, yes.
Okay.
Any other questions? Okay. So then the good news is the hardest part of the review is over for me. Those were the only two concepts that were not on any physics class I've ever taken before. So you guys are lucky. But the rest of this is very familiar to me, and I'm sure it's familiar to you as well. You're probably not as good as me at it, but who is? So we got position, velocity, and acceleration coming up. And just to give some quick definitions, position, I'm just going to call this X or Y. Position's pretty obvious. I'm not going to give an explanation for that. Change in position, I'm going to write more. Change in position, you can write delta X or delta Y, of course. But what this really is, remember delta X means X final minus X initial, or Y final minus Y initial. The delta means final minus initial. And we call this the displacement. We call this the displacement. Then we have average velocity. Average velocity has its own equation. V average equals delta x over delta t. In other words, that's just the displacement divided by the time. Very simple. And then finally, for average acceleration, A average equals delta V over delta t. In other words, the change in velocity over time. Change in velocity over time. One thing I got to remind you, because all my students forget at least at some point, and that is average velocity doesn't even have velocity in it. It's change in position. An average acceleration doesn't even have acceleration in it. It has velocity in it. That's because the average velocity and average acceleration doesn't have those quantities in it, even though it's in the name. But instantaneous velocity and instantaneous acceleration do. And to talk more about instantaneous velocity and acceleration, we're going to be looking at the actual graphs. Now here's a shortcut that they don't tell you in class, of course, why would they? But depending on the graph you get, you're only looking at one of three things. For the position graph, you're either looking at the y value, which you would be looking at for position. In other words, the y value is the position. Or you're looking for the slope, which is the velocity. And that's it. That's one of the two things you're looking for. If you're given a velocity versus time graph, then for that, the y value is actually your velocity, and that makes sense because it's the velocity graph. Your slope is the acceleration. And if you want to go back to position, that's when you use the area. You probably remember doing some area, but you don't know why. It's because you're finding the position. Actually, I'm going to change position just slightly, or at least if you want to write below, displacement, because that's really what it is. It's the change in position. And then finally, for the acceleration graph, there's only two things you look at. One is the y value, and of course that's the acceleration. And you'd never look at the slope for the acceleration. There's nothing higher than acceleration. But you can find the area, and that would be the change in velocity. Not just the velocity, the change in velocity. Any questions? Okay, then in that case, we have some graph questions coming up right now. Number 8, what is the velocity at 2 seconds? What is the average velocity from t equals 0 to t equals 6? So this is a position versus time graph, meaning if I want velocity, already using my notes from above, I know I'm looking for the slope of the position graph. So at 2, that's right here. Okay? And now one thing that you might make a mistake is you might try and find the slope just at that point only. Don't do that. If you want to find the slope of the whole line. It's a whole lot easier. And to find the slope, I use the equation slope equals y2 minus y1 over x2 minus x1. So I got to pick my 2 points. The first point's 0, negative 4, if I follow my y-axis. And the second point up here is, I guess that's 3. So 3, positive 8. So I got my 2 points. And now just plugging it in the slope formula, I get y2, 8, minus y1, negative 4. That will become positive. Divided by 3 minus 0. That's going to give me 8 plus 4 is 12 over 3. It looks like I got an instantaneous velocity of 4, and that's meters per second for this problem, because the graph had those units. Any questions there?
If it's asking for the velocity at a specific time, like 2 seconds, that's the instantaneous.
Yes.
So that's just the slope.
Yes. And okay. Look at this. If I ask for the velocity at 1 second, it's the same answer. If I look at basically any time between 0 and 3 seconds, it's the same answer. Because the slope is the same. And now average velocity. Remember, average velocity, don't you dare look at the slope. We just have to use this formula, delta x over delta t. Personally, I don't even like writing delta. I think it's confusing. I'm going to write x final minus x initial over time final minus time initial. Cut to the point. This is what it means. And we're looking at 0 to 6. We already have the point 0. The point 6, I guess, lines up with, that's positive 4. So that point 6, 4. Okay, great. X final's 4 minus x initial is negative 4 divided by 6 minus 0. You can just plug that in a calculator. You get 1.33 meters per second. And we're done. I almost guarantee you'll see a question just like that on the test. Anyone still writing? Okay. Next, number 9. Refer to the velocity versus time graph to answer the following questions. So again, this time it's velocity versus time. And I'm going to ask the audience for this one. Can someone tell me don't tell me the answer, just tell me what I'm looking for when I say instantaneous velocity at 5 seconds.
You just look at the y value
at exactly. 5? Yes, the y value at 5. Because it gave us the velocity graph. And so if I look at that y value right here, it's just 2. So 2 meters per second. And we're done. Very simple. Sometimes it's so simple it looks like a trick question. I get it. But you just got to follow the rules and you'll be fine. Next, part B. What is the instantaneous acceleration at 2 seconds? Someone tell me what I'm looking for instantaneous acceleration.
Slope?
Yes, because this is the velocity graph, so the slope is going to get me the acceleration. What's the slope at 2 seconds? It's just 0. It's no slope. 0 meters per second squared. Done. And then finally the last one, the hardest one. If the object starts at x equals 3 meters, what is its position after 9 seconds? Well, we already know. It's only one thing left. We already did y value and slope. It's got to be area. And we also know it's area because that gets us displacement. Remember, displacement is not the position. It's the change in position. So in other words, let's just say hypothetically I get an answer of 10. Then the answer is the initial, the starting point, 3 plus 10, 13. Don't actually write that down. That's not the answer. But I'm just saying the strategy is you add it to the original position. If it doesn't tell you an original position, assume it starts at 0 and you'll be fine. Okay, so now we got to find the area here. My recommendation, break it up into shapes. I got a rectangle over here in red. I got a triangle here in blue. And then I have another triangle down here for the last little bit. So first for the red, hopefully you know the area of a rectangle. It's base times height. So 4 times 3, which is 12. So 12 there. For the triangle, that's 1/2 base times height. So 1/2 base is 3. Just count. 4 to 7 is 3. And then count up to 3. 1/2 times 3 times 3, that's 4.5. Easy. And then the last one, again, is a triangle. 1/2 base is, count it, 2. Height is -2. The negative matters. And you'll get -1. Sorry, -2 as your area. And if you want to find the total displacement, you just got to add these numbers together. 12 plus 4.5 minus 2. You'll get 14.5. Remember, that's not the final answer. You got to add 3 to that to get the total position. And that gives us 17.5 meters. There's our final position. Any questions?
Going back to part B, I'm just a bit confused. Like, I know that the slope is 0, but like,
yes.
If you do rise over run, aren't you getting 3 over 3?
No, because if you say the rise is 3, that means you're going up 3 and right 3. So the rise is 0.
Oh, okay.
Yep. Any other questions? Okay. So next, number 10. It's a good one. Who am I kidding? They're all good ones. You guys are lucky. So, draw the position, velocity, and acceleration graphs for a car that is traveling at a constant speed of 10 meters per second. So, if you want to do this, my advice to you is start with velocity. Why? Because they told us the speed. Okay, we're going to start with velocity. You don't always have to start with position. I think that would actually be not a good idea for this one. So if it's a constant speed of 10, then that means at every time period it's 10, okay? So the y value is always 10 for this example. So in other words, the line is just a flat line across 10. And if I could draw a flat line, that'd be better, but I think you get the point. So there's our velocity. We don't have to go to position. Position's actually the hardest. The acceleration's very easy, because what's the acceleration?
0?
Yeah, acceleration is the slope of your velocity. And the slope of the velocity, it's 0 again. It's a flat line. So your acceleration is 0 everywhere. So just really bold that line at 0, and that's the acceleration. And now position's the hard one, because it's the area, but it's the area every second. What do I mean by that? So first, I didn't say it here. We're going to start at 0. I should have said start at 0. I left that out of the question. My bad. But if we start at 0, okay, and we want to know the position at 1 second, you got to find the area of this little square right here. And the area of that little square is 10. So in other words, my position is 10 at 1. And this is counting by 20, so 10 is in the middle. Okay, then the next area, if I want to find the position at 2, I got to find the area from 0 to 2. It's now a bigger rectangle. And that area is 2 times 10, 20. So at 2, it's 20. Then you do for the next one, and you're going to get 30. Then you do for the next one, you're going to get 40. And you see the pattern. You don't have to do all these, obviously. But the answer is it's a linear line, meaning that it's y equals mx plus b. And it goes up by 10 each time because I use the area for my velocity. So use area to find position. Does that make sense? Any questions?
So instead of like finding it for everyone, can we just assume because the line is staying the same that you're going to go up by the same amount every time?
Yes, that's right.
Okay.
Another connection you can make, by the way, hopefully you realize that since the velocity is the slope, that means the slope is 10. And you could have just drew a line with the slope 10 because that's what the slope is. That's another way of doing it. And again, I'd have to say the y-intercept is 0 or start at 0. For instance, if we started at 20, just shift your line up to start at 20, but still the slope is 10. Yeah, a lot of people, I think, either overthink it, sometimes they underthink it, but starting with velocity is definitely the way to go here. You can find everything from velocity, basically. Okay, next we're going to have number 11. Number 11 is going to start a series of questions that are more traditional and more math-based and calculation-based. So less conceptual in nature. A commercial airline flies 450 miles east at a speed of 300 miles per hour, followed by another 800 miles at 500 miles per hour. Part A, what is the total time of flight? I'm curious, does anyone think, just say yes or no. I guess if you say no, you don't have to say anything. But just say yes if you think you could do this right now without any help. I'm curious. Okay. So the secret for this one is this is a constant speed. It's a constant speed kind of problem. I mean, obviously it's not constant per se because it's two different speeds. I get that. But it's still constant speed for 450 miles, then constant speed for the next 800 miles. So in other words, what I'm trying to tell you is that whenever you notice it's constant speed, I want you to use this equation. Velocity equals distance over time. If you want, you can call it velocity equals delta x over delta t. It's the same thing. I don't care. But we're using this equation. So you also got to break this up into two parts because this is a two-part trip. For the first part of the trip, v equals d over t, my velocity is, it says 300 miles per hour. If the answer is, by the way, if this question's clearly all in miles and hours, so just keep it in miles and hours, okay? Don't convert the units this time. And then the distance, it said 450 divided by t. We're solving for t. I'm going to call this t1 because it's the first part. And using algebra, which again, I'm assuming I don't have to explain this, but please stop me if I'm assuming wrong. I'm assuming that you can solve for t1 and you get 1.5 if you do it correctly. So again, that's the first part of the trip, 1.5 hours. Now, for the second part of the trip, it says we're traveling 800 miles at 500 miles per hour. So this is the second part. V equals d over t again. The velocity this time is 500 equals the distance of 800 divided by t. This is t2 now. If you solve for t2, you end up getting 1.6. And obviously the final answer is just t1 plus t2. So 1.5 plus 1.6, we get 3.1, and that's hours. Any questions? Okay, now we want to find part B, which is what is the average speed for the flight? Now, average speed is technically different than average velocity, but luckily, since we're just flying in a straight line, it's not going to make a difference. I can explain what the difference is after this, but for average speed, it's the same thing as average velocity because we're flying in a straight line, and it's just going to be the total distance, which is called displacement, over the total time. Emphasis on total here because we have two parts to this trip. So what's the total distance? Well, if the first part of the trip was 450 and the second part was 800, just add these two together. And then divide by the total time. Well, total time is going to be the answer we just got, 3.1. And you plug this in a calculator and you just get 403.2, and that's miles per hour. Any questions there? Okay, now I'll just quickly address the difference between average speed and average velocity. I'm going to write that on a separate sheet of paper, so hopefully you have room to write this note. Average velocity is displacement over time, while average speed is distance traveled over time. Now, what's the difference between displacement and distance traveled. Does anyone know?
Isn't displacement just like where you started? Like if you walked like back and forth and you ended up in the same place you started, your displacement would be 0, but your
Yes.
distance traveled would be like actually the amount you walked.
Yes, you're exactly right. So just real quick, now I'll just go back to we're not actually going to do the problem, but if I go back to that walking 400 meters and then walking 300 meters at the angle, remember that one? Well, now we can talk about this. Because we said the displacement, in other words, the total distance, we got an answer of c equals 658.7. That was the displacement. But can someone tell me very easily what the distance traveled is?
$700.
Yeah, just 700. You just add the 400 plus the 300. You don't have to worry about any angles. We love speed. It's easy. So I'm going to go back now to the rest of the review, but are there any questions on anything from the past problem before we go to the next one? Okay, great. Next is number 12. Again, once again, yeah, whatever. I want you to try this one on your own. I'm going to give you about a minute and a half to try this. So go ahead. Okay, time's up. So first, if we want to find how far the box is pushed, and again, it's constant speed, then you just use v equals d over t again. Velocity is 2.5. The distance is what we're solving for, divided by 4. Multiply both sides by 4, you get d equals 10 meters. Hopefully you got that. Next, the average acceleration. This is a harder question, but all you need to do is use the average acceleration formula, which is delta v over delta t. And remember, delta v, that's the change in speed. That's the change in speed. Our speed was constant. So because we had constant speed, delta v was 0. So in other words, the average speed is 0 over 4, which is just 0. And yeah, that was kind of a trick question, but if you just followed the formula, you should have gotten it right. Any questions there? Okay, next. Next, we have a couple conceptual questions for you. This is what I was referring to earlier with the elevator. Number 12. Draw the velocity and acceleration vectors for someone in an elevator at the moment just before they reach the bottom floor. So, here's what we're going to do. We're going to have a fun game. And this is just at-home participation, okay? So you don't have to say anything. You don't even have to raise your hand or give a thumbs up. You don't have to do anything. Just think of this to yourself. Who thinks the velocity will point up? And who thinks the velocity will point down? Make your selection in your head now. And then who thinks the acceleration will point up? And who thinks the acceleration will point down? I suppose 0 is also an option, but I'll just tell you it's not 0 for this one. Okay, so hopefully you made your selection. And now I will explain for this elevator problem what to do. Also, I'm going to do a lot of writing, and I encourage you to as well, because I'm going to be explaining my entire thought process. First, if you want to find velocity, know that velocity is talking about the direction of travel. That's an easy way of thinking about velocity for problems like this. And which way are we going? We're going down because you're at the moment before reaching the bottom floor. So of course you're going down. You're going to the bottom floor. So there's my velocity, definitely down. Now, the acceleration. For acceleration, I gave the definition before of speeding up and slowing down. Obviously, it's slowing down because right before I shouldn't say obviously. I'll say it's slowing down because hold on. I need to write more clearly. I apologize. Slowing down. Okay, there. The reason why it's slowing down is because what happens right before you reach the bottom floor? You gotta slow down to a stop. And this is what I was saying earlier, that slowing down doesn't always mean acceleration points up or acceleration points down. In this case, it's definitely slowing down, and we know that because it's about to reach a stop. Slowing down, here's what slowing down means. Velocity and acceleration point in opposite directions. There, now you know what slowing down means from a technical standpoint. Velocity and acceleration point in opposite directions. Obviously, speeding up would therefore be same direction. Velocity and acceleration, same direction. So because it's slowing down, acceleration must point up. And there's the answer. Are there any questions?
So whenever we're trying to figure out if the acceleration should be positive or negative, just like see if it's speeding up or slowing down, and then relate it to the velocity to determine the direction?
Yes, for 1D motion. And the reason why I say 1D motion is because the next example is 2D motion, projectile motion, and we don't do that for 2D motion. You do something else. Anyone still writing? Okay, next, number 13. A quarterback throws the ball in the path shown below. Draw the velocity and acceleration vectors at points A, B, and C. So again, just take like 30 seconds, just think to yourself what the answer would be. Maybe you can even write it in if you want and then erase it if you're wrong. Okay, hopefully you've thought about it. Now I'm just going to tell you what we're going to do. So first, again, velocity points in the direction of travel. Velocity always points in the direction of travel. So what that means is at point A, velocity will point like that. At point B, velocity will point like that. And point C, the velocity points like that. Does that make sense? Okay, now for the acceleration. The reason why it's different for 2D motion, especially for an object affected by gravity, is that for 2D motion, acceleration always, and I mean always and everywhere, points down. So in other words, my acceleration points down at point A, points down at point B, and points down at point C. Doesn't matter which way it's going. Any questions there?
So is this because of gravity, like the acceleration for the projectile motion is always going to be negative 9.8?
It's exactly why, yes. That acceleration, we even know the quantity. It's negative 9.8, or you can call it negative g if you want. But g is a positive number. Any questions? And by the way, if you really understand acceleration, then you would say, Dan, I think I get it. As time goes on, the velocity is getting closer and closer to that acceleration vector. In other words, at first, think of it like a clock. At first, it's like pretty far apart. Then it's getting closer. Then by point C, it's almost, it's getting closer and closer. And if this were to theoretically go on forever, and there was no floor, eventually the footballs are going to hit the ground. But if there was no ground, eventually velocity and acceleration would point in the same direction, straight down. And that's why, by the way, that objects have this parabola shape. They're always trying to look more flat if it goes on for long enough. Any questions there? Okay, good. Next, we're going to talk about kinematics. We're going to go through kinematics, and then we're going to take that 5-minute break I talked about earlier. So, with kinematics, the first thing I want to say is, when do we use kinematics or projectile motion? We are going to use this, and remember, kinematics isn't always projectile motion. It can be 1D or 2D, but you use the kinematic equations when the acceleration is constant, not constant speed, constant acceleration. and the acceleration is non-zero. The reason why the non-zero part is important is because if it says constant speed or constant velocity, then the acceleration is 0. And if the acceleration is 0, you use this equation, which we said earlier. V equals d over t. So now I'm going to write the 4 kinematic equations. I know they're going to be given to you on an equation sheet, but just so we have them right now so we can go through them today, V initial equals V final plus AT. The next one is delta x equals V initial times time plus 1/2 AT squared. By the way, your equations might be written slightly different than mine, but as long as you've got the gist, it's going to be okay. Number 3, V final squared equals V initial squared plus 2a delta x. And then number 4, delta x equals 1/2 V initial plus V final times time. And I believe all 4 of these will be given to you. There's a chance that the last one will not be given to you, but if it's not given to you, it means you don't need it. And now what I want to say is, specifically for projectile motion, which is 2D kinematics, we have a strategy for projectile motion, and that is splitting things in the x-axis and the y-axis. You need to do this. So for that football example, if I wanted to actually solve it, I would split it up in the x and y-axis. I'm going to start with the y-axis because it's actually easier. I write out V initial y, V final y, acceleration, time, and displacement, delta y. And then, you use kinematics, very straightforward. X-axis, not so straightforward. The acceleration's 0 in the x-axis. The reason why is because the speed is not changing in the x-axis, only the y-axis. And so that means you use this equation, velocity equals distance over time, which I'm just going to write slightly differently. I write Vx equals delta x over t. And whenever you do a projectile motion problem, it'd be very wise to figure out what the x-axis velocity is and what the y-axis velocity is, because I guarantee you're going to need to know that. And it differs for each problem. Any questions? Okay, now let's do some example problems. Number 14. A jet flying 1 kilometer above the ground flies horizontally with a speed of 225 meters per second. If the jet drops a care package for a hospital directly below, how far will the care package overshoot the hospital? This is kind of a funny example. So you have a jet, and I'm actually half decent at drawing airplanes. Looks like an airplane. And it's flying over a hospital. It is 1 kilometer in the air, or 1,000 meters. I can write that too, 1,000 meters. And it drops a care package. Now, since the plane's going at 225 meters per second horizontally, it means that the care package is not going to drop straight down. Oh no. It is going to miss it, and it's going to look like this. So they should have done a better job when they delivered this care package. But we want to find this distance, delta x, that the care package missed. And that's what we're going to solve. So again, what I'm going to do is I'm going to split up the x-axis and the y-axis because they do different things for the different axes. It doesn't matter which one you start with. I like solving for the y-axis first, personally. I think it's a good idea to start with the y-axis. So for that, I say V initial y, V final y, acceleration, time, and displacement, delta y. And then I think about these variables. So of course, V initial is the 225. And now someone tell me why that's wrong. And you have to erase it. Because that's not the y-axis velocity. That's the x-axis velocity. Look at this. It's pointing straight to the right. That's x-axis, or x-hat if you want to call it that. Then what's the y-axis? It's 0. It's not going up or down at the start. So it was a trick question. Next, v final y. Well, obviously that's 0 because when it hits the ground it's 0. And now someone tell me why that's wrong. And you have to erase it again. Because the speed's not 0 when it hits the ground. We don't know the speed when it hits the ground. We don't know that. Obviously, when the care package is on the ground, its speed will be 0 after a long time. But we're saying what is the speed as it hits the ground or right before it hits the ground. And that we don't know. Acceleration, do we know that? That is the negative 9.8 because it's the same for every problem in the y-axis. Negative 9.8. And then time we don't know. And delta y is 1,000. And now because I want you to hate me, why is delta y not 1,000? Don't erase it. It's not completely wrong. It's not because of Pythagorean theorem. I'm just saying if you say it's 1,000, you're saying the care package goes up 1,000 meters. It went down, so it's got to be negative. And that's important because if you miss that negative sign, then you're probably going to get the wrong answer mathematically. Okay, now for the x-axis. For the x-axis, I just have one equation. Vx equals delta x over t. And I know my velocity because that's the 225 number. 225 equals delta x, and I don't know time either. And I'm solving for delta x, which means I need the x-axis. But I also need the y-axis because the y-axis is going to get me my time. The question is, what equation am I going to plug into to get that time? And the answer is the second equation. And that is delta y equals v initial times time plus 1/2 at squared. So like we said, delta y is negative 1,000. V initial is 0, so the time does that part just goes away. Plus 1/2 times negative 9.8 times t squared. So then simplifying this, I get negative 1,000 equals negative 4.9 t squared. Divide by negative 4.9. I'm going to get 204.0 equals t squared. Positive, by the way. It would be negative if I missed that earlier. And then I got to take the square root. T equals 14.3 seconds. I've got my time. Remember, time is not the final answer, but it is necessary that we got that so I could then solve for delta x. Because then going back to delta x, we said that Vx equals delta x over t. That velocity is 225 equals delta x over the time we just found, which is 14.3. And if you multiply by 14.3 on both sides, you'll get your delta x, which is 3,214 meters. Wow, we really missed the hospital. And that's why when care packages are dropped from helicopters, well, first of all, you don't just drop them. It's usually like, gradually drop. They don't just throw it out. Although they do that for bombs. Bombs are like that. You don't casually drop a bomb. So, bombs would be a more realistic example of the plane example. But care package was less violent, so I went with the care package. Anyways, that's it. Any questions on number 14?
So if you did end up getting a negative time, could you just assume that you forgot the negative sign for the delta y and just make the time positive?
Yeah, so let me tell you what would have happened specifically. You would have had a negative here, and your calculator would say error, and then you would have just tried making that positive, and then you'd get the right answer. Of course, that'd be a red flag to you, so you should still check your work when that happens, and you'll see that you missed the negative on the height. Now, that works sometimes, and it will not work all the time. A good example of that is number 16, which is the next problem. Oh, Well, we have to do 15 first. Whatever. And then we'll do 16. Number 15, rank the balls by which will hit the ground first to last. Okay, which will hit the ground first and which will hit the ground last. You'll notice I give the velocities in x hat and y hat notation, which is fair game. Now, what am I looking for here for the x-axis and y-axis and all this stuff? I don't even have a height, right? Well, I'll tell you this. When you want to find the time of flight, especially because, you know, it's all the same height here, it's whatever this height of this building is. If you're looking at the time of flight, you want to know which y-axis velocity is the greatest. In other words, I don't care about the x-axis at all. I'm not going to be doing Pythagorean theorem. I don't care about it. If I want to find time of flight, I'm just looking at which y-axis velocity is the greatest. So in other words, for A it's 4, for B it's 3, and for C it's 3. So if I want to list them from least hit the ground first to last, B and C are at the same time, and then A will hit last. And there's our answer. Any questions? Okay. And then number 16 is going to be the last one before our break. A golfer hits a ball with an initial velocity of 44 meters per second at an angle of 60 degrees above the horizontal. The ball lands on the green, which is 10 meters lower in elevation. What is the speed of the ball when it hits the green? So first I'll draw a picture of this. I basically have a ball on a surface being hit, and it lands on the green, which is 10 meters lower in elevation. If you want to write negative 10 right now, I encourage you to. And it's gonna land somewhere around here, whatever. The ball was struck with an initial speed of 44 meters per second at an angle 60 degrees above the ground. And we want to know the speed of the ball when it hits the green. Okay, so we're solving for V final, it sounds like. Great. So the first thing I'm going to do, before I even do anything with the x-axis and y-axis, as soon as I have an angle at a vector, like speed, at an angle, 60 degrees, I need to split that in x and y components. So in other words, Michaela Sauce, raise your hand. Michaela, for the future, just call out. What's up?
I was just gonna say that we can't hear you. Or
Can
at
you
least
hear
I
me?
can't.
Can you hear me now?
A little better?
Can everyone else speak on that? Is this just a Michaela problem, or is this everyone?
I can hear you.
I can hear you.
Okay.
I can.
Thank you. Michaela, by the way, if you cannot hear me, the good news is the audio will be perfect. So anything you don't hear me, you can just listen to again during the recording. Okay?
Okay, thank you.
Yep, no problem. Can you still see my screen okay, by the way? It's still like writing, right?
Yeah,
Okay,
I can
good.
see this.
Good. Okay, then. So the first thing I got to do is I got to draw a right triangle, and I got to split it up in the x and y components. That's the first thing I do. This is 60 degrees. This is 44. So again, cosine's going to be the adjacent, which is x. And write small for this one. This is like a pretty big problem. But cosine 60 degrees equals x over 44. So that means if I solve for x, 44 cosine 60, I get 22 exactly. And then if I want to solve for the y, I would say sine of 60 equals y over 44. And if I solve this for y pretty easily, I get 38.1. Now just so you know, this is my Vx and this is my Vy initial, because it's the speed that I'm striking the ball with. It's not the final, it's the initial. So now, when I go to my x-axis and y-axis, and again, I like to start with the y-axis. I'll do that now. And I have v initial y. That's the number I just said, 38.1. v final y. That's what I'm solving for. I want the final speed. The acceleration is still negative 9.8. That didn't change. Time is unknown. And who knows what delta y is? Negative 10. Negative 10. And now what's funny is I actually don't even need the x-axis for this problem. Why not? Because I'm solving for v final y. I don't even need the x-axis. Great. So which equation am I going to plug into to solve for v final? It's the equation that doesn't have time in it, because I don't know what that variable is, which is the squared one. V final squared equals v initial squared plus 2a. Instead of delta x, I'm going to write delta y. It's the same thing. So then that means v final squared equals v initial squared, which was the 38.1 squared, plus 2 times negative 9.8 times negative 10. And if we miss that negative sign this time, you will get the wrong answer and you'll have no idea that you got the wrong answer. So then simplifying the right side, v final squared equals 1,647.6. And then I just got to take the square root of that. Remember that when you take the square root in math, you get plus or minus. I really don't care because I would make it positive anyway. But the reason why I want to mention this is because we'll get an answer of 40.6. And technically that should be negative 40.6 because the ball's going down, like into the ground. Now again, as long as you remember it's going down, I don't care if you say the positive or negative or whatever. But just recognize that the ball's definitely going down. And there's our final answer, 40.6. And someone tell me why this is not the final answer. I bet you're thinking, shoot, I thought that was the final answer. Yeah, no, because you just found the y component. You found vy, we saw vx. So vy is negative 40.6. Vx is still the 22 we found from the beginning. Because if you think about it, this final speed, let me just draw the picture again. This final speed is pointing down at an angle, isn't it? Which means I got to find vx, I got to find vy, which luckily I already did. And now I just got to use Pythagorean theorem to solve. Vx squared plus vy squared equals v final squared. And we have all these numbers. So 22 squared plus, this is what I was saying earlier, like I don't care about the negative because as soon as we square it, it's going to become positive anyway. So then if I solve for v final in the Pythagorean theorem, I get 46.2 meters per second. And there's our final answer. Any questions on that one? Okay, anyone still writing? Okay, good. Then here's what I'm going to tell you. We're going to take a 5-minute break. We're going to continue at 1:59 or probably 2 o'clock, okay? I'll say 2 o'clock. We'll get started again. And when we come back, we're going to be doing rotational motion, which I'm pretty sure is not on most of your exams. Is that correct? For your professors?
I think it's only on Dr. Navros's exam.
Gotcha. So just out of curiosity, is anyone here from Dr. Navros? Okay. I know I have other students who are definitely going to watch the recording, so I can't skip it. But I will tell you this. That's going to take me about 15 minutes. So if you want to reconvene at like 2:15, like don't go anywhere. Just like mute it or whatever. But I'll tell you by about 2:15 we should be done angular motion, especially because I don't have to stop for questions or anything. So maybe even like closer to 10 minutes. But by 2:10 you should be back on the recording, and then we'll finish up with forces. Okay, so break begins now. Oh, and if you have any questions, you can ask them as soon as I come back, because I gotta pee. Okay, I'm going to get started back up. And again, this is the rotational part. So if you have Dr. Navros, then this applies to you. If not, we'll probably continue again at like 2:10 or in like 10 minutes. So you can just jump ahead to the part where we get, if you're watching the video, you can just jump ahead to the part where we talk about forces. And just so you have an idea for how much longer we have, because I know it's already been 2 hours, I think we're going to be done around 2:30 or 2:45. There's not too much left. Okay, so here's what I want to say about angular kinematics. First of all, remember how we had v initial, v final, acceleration, time, and delta x? Well, these variables get replaced with their angular counterparts. Omega initial, omega final, alpha, still time, and delta theta. And the thing, oh yeah, and it's the same equations. Definitely the same equations, so that's nice. And the only other thing I have to say about that is that we have the tangential or the linear world of physics. And now we're going to introduce the rotational, also known as the angular side of physics. And for that, we're going to use some equations that relate the two worlds and bring them together. The first one is Vt, tangential velocity, equals omega times r. And the second one is At, tangential acceleration, equals alpha times r. In other words, the radius combines the two worlds and brings them together. And with that, we can talk about centripetal acceleration too, because that has its own equation, AC for centripetal, equals v squared over r. This is the tangential velocity, again, Vt, and it's we call it the tangential velocity. And all the tangential velocity is if you were like a cop, and let's say you had a speed gun and you were clocking how fast the cars are going, that's what the tangential velocity is. It's how fast your speedometer says you're going, okay? So, one more thing I want to say about this is, what is centripetal acceleration anyway? Well, if I draw a circle, and let's say a dot or a car or whatever is here, then you have two kinds of acceleration going on. You have a centripetal acceleration, which always points towards the center. This is the acceleration that keeps you moving in a circle. And then the other kind of acceleration you have is AT, and that stands for tangential. It's going around the circle. And if you want to find the total, well then, once again, we need like Pythagorean theorem to find the total acceleration, because we love the Pythagorean theorem so much. So then with that, let's look at some example problems. Number 17. 2 pennies are placed on a spinning wheel rotating at a constant speed. Which penny has the greater angular velocity? Which penny has the greater tangential velocity? And which penny has the greater angular acceleration? So first we're going to answer the angular velocity question. And what most people answer the first time they see this question is they'll say, oh, well, B is faster because it's on the rim and the radius is bigger. But you're thinking about it wrong, because angular velocity omega, I want you to think of omega as delta theta, change in angle, over delta t, change in time. Now here's the thing, when they go around this circle, it's the same angle. Like, definitely the same angle, because you can't go around one penny without moving the other penny. They got to be moving together around the circle. And it's the same time. And because it's the same angle and it's the same time, that means the angular velocities are the same. Now, for the tangential velocity, these will not be the same. This is what you are probably thinking of for angular velocity. Tangential velocity, we can just use the equation Vt equals omega times r. Remember, we said omega was the same for both, but obviously the radius is not the same for both. The radius b is larger for radius, which means that the velocity b will have a greater tangential velocity. And that's because it has a larger radius. And then the last thing we want to solve for is the angular acceleration. So for that, angular acceleration, the symbol for that is alpha. And alpha, if you want an equation, is like delta omega over delta t. And remember, if the angular velocities were the same, like we said in the last page, then that means the change in angular velocities also have to be the same. Again, it's the same time too, which means that alpha is going to be the same for both as well. So they're all the same, at least for alpha. And tangential velocity was bigger for the B. Okay, next we have number 18. A 20 centimeter diameter wheel speeds up from rest to reach a final angular speed of 25 radians per second. What is the total acceleration of a piece of gum stuck to the rim of the wheel after 6 seconds? So if we want to find total acceleration, hopefully you know I want AT and AC. So that means it doesn't matter the order I find them. I'll find tangential first. And for that, I got to plug in my kinematic variables. Omega initial, omega final, alpha, t, and delta theta. So it says I'm speeding up from rest. That means the initial 0. The final speed of the wheel, it says 25 radians per second. Even if you don't know what a radian is, don't worry about it. But just know that we like those units. We like radians per second as our units. We're solving for alpha, the acceleration. Time is 6 seconds, says it in the problem. And delta theta we don't know. And nor do we care because we have 3 of the 5 variables already. It means I'm going to just plug into this equation. Omega final equals omega initial plus alpha t. So 25 equals 0 plus alpha times 6. And if we solve for alpha, then we're going to get alpha equals 4.167. And that's radians per second squared as the units. But that's not the tangential acceleration. To find that, we use that equation we said earlier, which is AT equals alpha times r. Now be careful, because I said a 20 centimeter diameter. I'm really trying to trick you here. Because first of all, centimeters needs to be converted to meters, so 0.20. And then diameter is not radius. Got to divide that by 2. So if you take 20, divide it by 2, and convert to meters, it's a 0.1 meter radius. 0.1 meters. So that means AT is going to be alpha, 4.167, times the radius, which is 0.1, and that will just be 0.4167. And now the units are back to meters per second squared. We still got to find AC. So to do that, here's what I would do. AC equals V squared over R. I have the radius, but I don't have the velocity. However, I can easily find the velocity, because remember, velocity equals omega times r. We have omega. Omega is just going to be the 25 because that's the instant we're talking about. We're talking about the final. So 25 times 0.1, you get 2.5. And once you have the velocity, this is very simple. It's 2.5 squared over 0.1. And you plug that into calculator, and you'll get 62.5 meters per second squared. And once again, if you want the total, then you just got to take the Pythagorean theorem sum of AC squared plus AT squared. So in other words, that's the square root of 62.5 squared plus the other one was 0.4167 squared. And that's such like a small number that it actually doesn't change your answer at all. The answer is 62.5 meters per second squared. And that's our total acceleration. And then the last question we have for any of the angular stuff is number 19. And it's a really fun, simple question. I just want to know, what is the angular speed of the minute hand of a clock? A very fun question. So if you want to find the angular speed, first of all, I want you to know that it's a constant speed. Because the minute hand is moving at a constant speed. It's not speeding up or slowing down. Or else you'd have a real problem with your clock. It wouldn't be very accurate if it was speeding up or slowing down. So then that means we're going to use the equation omega equals delta theta over t. Where have we seen this equation before? V equals delta x over t. It's like the same equation as that. And delta theta is 1 revolution. Now we need to know how to convert from revolutions to radians because we need our answer to be in radians. So 1 revolution equals 2 pi radians, and that's a conversion factor you should know. So then that means omega, which is what I'm solving for, equals 2 pi radians divided by the time. Now, how long does it take a minute hand to go around a clock? It's a simple question with a simple answer. And the answer is 60 minutes. That's right. Such a fun problem. Now, I can't have my answer in minutes. I got to convert that to seconds. So, times 60 minutes times 1 minute and 60 seconds. So I'm just multiplying by 60. And that'll be 3,600 seconds. So I'll put that instead for my denominator. 3,600 seconds. So then omega equals 0.0017, and that's radians per second. And that's the answer for that problem. So then if you are in Navros's class, this is basically the end of the review for you. The rest of the problems will be on forces. And for those of you still there, I'm going to now talk more about your stuff, which is we're going to end with forces. And look at that, 210 on the dot. Am I good at or what? I said that grammatically wrong. Hold on, let me try that again. Am I good or what? Don't answer that question because I think I'm losing my credibility. So anyways, with forces, we're first going to talk about Newton's laws. And I'm not going to, maybe I'll say Newton's laws, but I'm not going to write down word for word what they are. Like, for instance, Newton's first law is an object in motion stays in motion, and an object at rest stays at rest unless acted upon by an outside force. Now, what does that really mean for us? It means that if I have constant velocity, and we all know what that means, then that means my acceleration is 0, and more importantly, my net force, F net, is 0. And by the way, these arrows go both ways, meaning that if one is true, then all 3 are true. You can find the acceleration 0, and then all of a sudden you know the net force is 0, and you're at constant velocity. And that's basically what Newton's first law is saying as an equation. Newton's second law is probably the most famous equation in all of physics. It's F equals ma. But I never write F equals ma. Instead, I always write this. I say F net x equals all the forces pointing right minus the forces pointing left. And that equals ma x because it's the x velocity. And then we can do the same thing for F net y, the y component of velocity. F net y is equal to all the forces pointing up minus the forces pointing down. And that equals mass times acceleration in the y direction. Now, of course, before we use the equation, we probably got to do a free body diagram first, but that's coming later. And then Newton's third law. Newton's third law says every force has an equal and opposite reaction force. And what that means for us as an equation is if you have a force of 1 on 2, then it must equal the force of 2 on 1. Now, one thing that's kind of confusing about this is that I remember when I was in physics, I was like, wait a minute, equal and opposite. That means one of these should be negative. No, don't do that. Keep them both positive. The reason why is we already took care of the negative. What do I mean by that? Using Newton's second law, you would basically say force 1 on 2, which points in the positive direction, minus force 2 on 1 in the negative direction, equals mass times acceleration. And if these two forces cancel each other out, that means the acceleration is 0. So in other words, force 1 on 2 minus force 2 on 1 equals 0. And you just add 2 on 1 to both sides. That's how I get this equation. So don't make one negative, because then you're making it like a double negative, so don't do that. It's already covered in this formula. Okay, next, we have weight and the force of gravity. Literally the same thing. The equation for weight is W equals mg. The force of gravity, which I call Fg, is also mg. It's the exact same thing, or at least it has the same equation. So our weight is the force of gravity. And the only way you're going to change your weight, besides obviously like gaining or losing weight, but like I'm saying the only way that it would not be mg is if you changed planets or something, because then g is no longer 9.8. They'd have to tell you what g is in order to solve it. And then the normal force. The normal force, it always points perpendicular to the surface. Perpendicular to the surface. By the way, that's what the word normal means. It's kind of weird. Like, you probably never thought, like, why do they call it the normal force? That's a weird name. Because normal means perpendicular. And then you ask, well, then why don't they just call it the perpendicular force? Because I wasn't in the room when the physicists came to decide this, okay? Or else I would have called it the perpendicular force, believe me. And just to give a quick example, if I have a box on a flat surface, then the normal force points up. And if I have a box on a ramp like this, then the normal force points up and to the right, like that. It's always perpendicular to whatever surface you're on. And now we're going to talk about how to solve force problems. It's a 3-step process. The first step is you're going to draw a free body diagram. Remember, the free body diagram is like the box with all the forces on it, and your professor does something really silly, in my opinion, which is you'll call it, for instance, if I have like a box, then you call it the weight of the object, Earth, on the box, and then you got normal force and ground on box. I hate those little subscripts. I think it's the dumbest thing in the world. I think it's confusing and not helpful at all. And if I was grading this and I was like, oh, well, this is a cardboard box, so I got to call it NGC, and that's not the ground, that's dirt, so it's really DC. And if I'm looking at this NDC and I have no idea what the D and the C were because no one defined them, I think it's the dumbest thing in the world. I hate it with a passion, and I really thought I never had to do it again. And when I say again, they never did it before at University of Delaware. I only saw it one time in my life, and it was for like some weird like high school kid. The kid wasn't weird, the school was weird. And I hated every second I was with that kid. Again, not the kid, it was the forces. So anyways, before we even get to step 2, we have a step 1.5. And step 1.5, which is extremely important, is to split forces at an angle into x and y components, just like we did for velocity and kinematics and projectile motion. After you do that, then we're at step 2. And step 2 is the f net x and or f net y that we just said earlier. And then finally, step 3 is we're going to solve using algebra. If you did steps 1 and 2 right, then step 3 should be a breeze. So the hard part is steps 1 and 2, and step 1.5. Okay, here we go. We have a nice conceptual question for us with number 20. How would an object's mass and weight change if you moved it to the moon, where the gravity is 1/6 as strong as Earth? Does anyone want to take a shot at this?
Do you multiply 9.8 times 1/6?
Yes, so 9.8 times 1/6. And again, so that's your weight, because weight equals mg. Gravity changed. And the mass, mass is still mass. So weight decreases by 1/6. That's how your weight changes. And then how about your mass? Would your mass change? And if so, by how much? So your mass does not change. And that's because mass doesn't matter what planet you are on. It doesn't matter if you're in outer space. It doesn't matter at all. Like, mass is going to be a constant no matter where you are. Which then brings a fun question for you guys. And I'm not going to answer this question today, but I will answer it later in the course. Maybe in the second exam review. But if you want to measure your weight, and you're an astronaut and you're on the International Space Station, how would you measure your weight? Because you better believe a scale won't work, because a scale only works if you have gravity. So how do you measure your weight if you don't have gravity? Any guesses? I don't expect you to know the answer, but I'm curious if there's any creative solutions. No creativity. Go ahead.
Could you figure like the forces on you and then solve for it?
I love that answer, and that is a creative answer. And let's say, in other words, you push someone with 100 newtons, and you have a way of knowing it's exactly 100 newtons, which you can do with a machine. And then you calculate the acceleration that they pushed, which you can use using kinematics, then yeah, you can calculate their mass. Now, as it turns out, the correct answer is even more interesting than that, although I love your answer. And we will find out the answer in the next exam review, probably. So, with that, we go to number 21. What would the acceleration and normal force be on a 12 kilogram suitcase that is being pulled with a force of 80 newtons at a 63 degree angle? First thing I'm going to do is I'm going to draw a picture of this scenario. Always a good idea to start with a picture. So we got a 12 kilogram suitcase, and it's being pushed 80 newtons, which I'll call FP on B, push on box. Why not? And the angle is 63 degrees. Now we're going to do the free body diagram. We know we have weight pushing down, weight of Earth on the box, and we know we have a normal force of the ground on the box. It's not even a box, it's a suitcase, but whatever. Now, there is no friction here, or else I would have mentioned it. I should have said frictionless surface. That was my bad, but whatever. And so if there's no friction, that's it. These are all the forces, and we're ready for step 2. Wrong. Step 1.5. We have a force at an angle. So for that, I'm going to take this 80 Newton force, break it up into components Fx and Fy, and that angle is 63 degrees. So again, this is basically something we've been doing all day, which means if I want to do Fx, I would use cosine. Cosine of 63 degrees equals adjacent over hypotenuse 80. And if you solve for Fx, if you solve for Fx, then you'll get 36.3. And the units are newtons, so newtons. And then if you want to find the y component, you just do sine. Sine 63 degrees equals Fy, opposite, over 80. And so then Fy is going to equal 71.3 newtons. So we have the x component, we have the y component, now what? Well, now I'm going to do F net x and F net y. I'm going to start with F net x. It doesn't matter which one you do, but I'll do F net x first. And that's going to be all the forces to the right, which is really only Fx. Fx is the only force that points to the right. There's no forces to the left, so minus nothing. And then that equals the mass times the acceleration. Now we know Fx, it's 36.3. We know the mass, it's 12, which means A is very easy to solve. A is going to be 3.0 meters per second. And there's our answer. Oh, meters per second squared. What am I doing? Any questions on the acceleration? Okay, now I got to find the normal force. Now here's the thing. Normal force usually is just mass times gravity. But it's not this time, and we'll see why. So if I want to find the normal force, I'm going to say F net y equals all the forces going up. That's NGB plus Fy, because Fy also points up. And then minus the forces pointing down. There's only one, minus WEB. And that's going to equal mass times acceleration. But that acceleration we know. And it's not the 3 we just got a minute ago, because this is the y acceleration. And is this suitcase moving up or down? Probably not. It's probably moving across the floor, like flat. So for that reason, it's not moving up or down. Acceleration 0 in the y direction. So I want to solve for NGB. We just found Fy. It's 71.3. And then minus mg. Weight is mg. 12 times 9.8. And then that equals 0. So now if I solve for NGB, I'm going to add 12 times 9.8 to both sides and subtract 71.3. And that'll get us a final answer of 46.3, and the units are newtons. Any questions there? Okay, good. Just a few more questions to go. We're almost done. Next is number 22, a conceptual question. Which of Newton's laws best explains why a revolver kicks back after you fire it? Any guesses?
Is it the third one?
Definitely the third one. Let's explain. The revolver kicks back due to Newton's third law. Because, now I'm just going to talk for a second before I write anything down. It's Newton's third law because Newton's third law says every force has an equal and opposite reaction force. So when the bullet gets fired forward, the revolver gets fired back. And so what I'm going to write is, because the force causing the bullet to move forward also causes the revolver to kick back. Those forces are equal in magnitude and opposite in direction too. I'm not going to write that, I'm already out of room, but you can if you want. Equal in magnitude, opposite in direction.
So he also talked about this thing in class of like a third law pair. Could you explain it by just saying the forces
Yes.
are a third law pair?
Yes. And if you say the third law pairs are the bullet going forward force, or the gunpowder force, or whatever you want to call it, and the recoil force of the gun, that's what I would say. And one more thing I want to say about those pair forces. You'll notice we didn't have any pair forces on the last problem. In other words, with the box. And you could say, well, isn't the normal force and the gravity force pair forces? And the answer is no. And let me explain. Because our free body diagram should never have pair forces if there's only one object. Pair forces only show up if you have two or more objects on the free body diagram. And if I were to explain that just real quick, here's the box again, and here's the Earth. And the free body diagram on the Earth is the box is pulling it down, WEB, and the box is also pulling up on the Earth with W box Earth. But I'm not drawing a free body diagram for the Earth, so this force never gets seen. And if you include it, then you're just wrong. Okay, any questions on that? Okay, next, number 23. Another one of the same kind of questions. Which of Newton's laws best explains the motion of a satellite in deep space? So I would say, and why?
Why it's the second one?
Yeah.
Because that has to do with the gravity.
That's the thing. When you're in deep space, there is no gravity. This thing's just floating out there without touching anything. Now, I would say you'd be right. If it would be Newton's second laws if there was an acceleration. But there is no acceleration here. And that's the thing that you need to know about this satellite. Like any object floating in space, you probably know this as well as I do, it's floating aimlessly in space without any, gravity affecting it. So for that reason, what I'm going to say is this is due to Newton's first law. Remember, Newton's first law talks about the acceleration being zero and constant speed. So what I'm going to write is this is due to Newton's first law because the satellite's speed is not changing. This is because there are no forces acting on the satellite. Any questions with that one? Anyone still writing? Okay, then all that's left to talk about is friction, and there's just a couple more questions to go. So first, we'll talk about static friction. So static friction is not moving. And the equation, there's two equations I'm going to give you. The first one is Fs, I don't know what you call it, but I call it Fs, is less than or equal to mu s times the normal force. The reason why I say less than or equal to is because it changes depending on how hard you're pushing. Like if I push on my bed, which is right next to me, with 10 newtons of force, it's not going to move. But if I push with 20 newtons of force, it's still not going to move because that's not very strong. And you probably don't know that. But yeah, 10 newtons, 20 newtons, not going to move. I don't know how hard I have to push it, but that's not the point. The point is the friction force, when I pushed with 10, the friction force was 10. When I pushed with 20, the friction force was 20. It always matches your pushing force until you actually start moving. At the instant you start moving, you become kinetic friction. And so the only thing I want to say is that there is a point in between static and kinetic. It's literally the point at which it switches over. We call that the max static friction force, and that's the only time you get to say equals to. Also, that variable right there, that's called the coefficient of friction. Coefficient of friction. And it depends on what surface you're on. A very high coefficient of friction, like 0.9, 0.8, means it's a very rough surface. A very low coefficient of friction, 0.1, 0.2, is very slippery. And usually the value is between 0 and 1 for coefficient of friction. Okay, now kinetic friction. Kinetic friction, we're moving. And there's just one equation and it's great. Fk equals mu k times the normal force. And that's it. And as far as the direction of friction goes, the thing we need to know is that friction always opposes motion. Friction always opposes motion. And
I have
with
a question about that.
Absolutely.
So our professor always says friction opposes slip. Could you
Yes.
explain that? Like
Yes.
because he says there are some cases where it doesn't oppose motion. And could you give an example?
Absolutely. So friction that's actually a good way of putting it, actually. I like that. Friction opposes motion, that's a great way of describing kinetic, okay? Because if you're moving to the right, friction points to the left. Static friction, I like what you said about that because obviously you're not moving if it's static friction, right? But you're opposing slip, and what does that mean? So if I push to the right, why doesn't the bed push to the right? Because it's not slipping to the right, because it's pushing left. That's what it means.
So you're saying if you're trying to push your bed to the right, but it's not moving, so there's static friction, the static friction would point to the left.
Yes, and even if I push so hard to the right that my bed started moving, now I'm moving to the right, friction opposes motion, friction still points to the left.
Okay.
Does that make sense?
Yeah, that makes sense. Thank you.
Yep, and we'll have a good question on that too with the last question of the day, 25. But now we have 24, which is kind of a conceptual question. A man pushes a box across a floor with kinetic friction. In the following scenarios, determine if the kinetic friction would increase, decrease, or stay the same. Okay, part A. The box is pushed twice as hard. Just don't say it out loud, just think it in your head for a second. Increase, decrease, or stay the same. I'm assuming you have your answer. The answer is, it will stay the same. And before you grab your pitchforks and say why, you didn't even give me a chance to explain. So, what's the equation for kinetic friction? Fk equals mu k times the normal force. So as long as these two variables are staying the same, then it doesn't matter, the friction's going to stay the same. Remember, the coefficient of friction, that depends on your surface, and the surface didn't change. And your normal force basically depends on the weight of the object, and that didn't change either. Neither of these things changed, so it stayed the same. What will change when you push twice as hard is the acceleration, but I'm not asking about the acceleration. So friction stayed the same. Okay, part B. You push the box across an ice rink instead. Again, same thing. Think to yourself, increase, decrease, or stay the same. The answer is it will decrease. And the reason why, the ice rink is definitely going to be slipperier. That's the right word. Slippier. I guess slippier.
Slippery,
And it's
more slippery.
more slippery. We're going to go with more slippery today. And because it's more slippery, mu k went down, decreased, which means friction decreased. Okay, part C. You stack an identical box on top and push both. Again, think to yourself. And the answer is it will increase. And the reason why is because going back to the equation, mu k times the normal force. Mu k didn't change because obviously it's still the same surface, but the normal force got bigger. Let me explain. If I have mass here and a mass here, the weight had to increase, weight, earth on box, which means the normal force also must have increased, ground on box. And because the normal force increased, that means that the whole thing's going to increase. Any questions? And then finally, one more. Here's a fun question for that example I just said, actually, because this is a good conceptual question too. So mass here, let's say I push the bottom box to the right. Okay, this is not obviously on the exam, but it will be on the exam, I think, or something like it, but maybe. What I'm trying to say is this is not part D, I'm still in part C. But which way will friction point for each box? I will tell you. Friction will point to the left for the bottom box, and that's kinetic friction, because it's opposing motion. The motion pointing to the right, the friction pointing to the left. For the top box, this is the confusing one. Because the top box, and by the way, whenever you have a box on top of another box, like these kinds of problems, which is what 25 is, it's the most difficult kind of friction problem, which is why I want to take a second to talk about it. So for the top box, it's actually not moving. The top box is not moving, which means it's not kinetic friction. Of course, for part C, I was talking about the kinetic friction here, which definitely increased. But there is static friction for the top box. If there was no friction, the box would just slide off. And that's the thing. If there was no friction, the box would slide off that way. So friction, static friction, must point that way. Isn't that confusing? So static friction points to the right for the top box. Kinetic friction points to the left for the bottom box. Any questions?
So I think something like this will be on the exam, but he's not going to make us solve it. He said it's going to be more conceptual. So
Yes.
One thing I always get confused on, even though I know, I just get confused is the F force, the pushing force, is when you draw the free body diagram for the top box.
Yep.
Does that, do you have to draw that for the top box or just the bottom?
Here's what you would do. But that's a good question. So for the top box, I've got gravity pushing down, weight. I've got a normal force pushing up, and I have a static friction pointing to the right, and that's it. The bottom box is actually a mess because it has a lot of force. It has a lot of forces it has to deal with. So first, it's got a pushing force pointing to the right. It's got gravity pointing down, or weight. It's also got a normal force pointing down from the other box, and that's the Newton's third law pairs. Remember how I said earlier, you only see the Newton's pairs if you have two boxes or two objects? This is where you'd see it. So normal force points down because the other normal force pointed up. We've got a kinetic friction pointing to the left. We've got a normal force pointing up, and this is the normal force from the ground to the box, and I guess you'd call it box one. And there are two different normal forces, just to be clear. One normal force is from the ground, one normal force is from the box above it. They point in opposite directions. And then there's one force we're missing. It's the static friction from the top box, because that's a paired force too, believe it or not. And that points to the left because it's the opposite direction as the top box. I told you, the bottom box is a mess. But this is all the forces. So if you see a question like this and you don't understand what's going on, just memorize what I just said and you'll be fine. Any other questions?
I just have
yes,
a couple questions about friction, but I could ask it like after.
Yeah, just ask it after. We're almost done anyway. Okay, part D. You push the box with half the velocity as before. Does not show up in the equation. No change. Stays the same. Because again, friction is mu k times the normal force, and that's neither of those is velocity, so it doesn't matter. Any questions? Okay. Then next, the last problem of the day, 25. A pickup truck has a crate of apples in the back. The coefficient of static friction between the crate and the truck bed is 0.3, and the coefficient of kinetic friction is 0.22. As the truck approaches a stop sign, it comes to a complete stop in 20 meters, and the crate of apples doesn't move. What kind of friction was displayed in this example, static or kinetic? Which way did the friction point? Toward the front or the back of the truck? What was the maximum speed the truck could have been going without the crate slipping? We'll do these one at a time. First, is it static or kinetic? Definitely static, it's not moving. And by that, I mean the crate of apples is not moving. Like, obviously you can say there was friction between the truck and the road, but we're really not focusing on that. We're talking about the crate of apples in the back, and that's not moving. For the next question, which way did the friction point? Toward the front or the back of the truck? For that, I'm going to draw a picture of what's going on here. So here's my truck, and here's my crate of apples. Okay, and it doesn't slip. Just think to yourself, do you think do you think the friction's pointing forward or backwards? And this is a tough question, but the answer is, before I give you the answer, I'm going to give the explanation this time, like I probably should have in the last question, but whatever. So, which way is the truck accelerating? The truck is accelerating to the left. How is it accelerating to the left? Because velocity points forward. Opposite direction, slowing down, remember that? So because the truck's slowing down, acceleration must be pointing left. Now let me think of the forces acting on my apples. I got weight going down, I got a normal force going up, and there's no other force, besides friction, there's no other forces acting on it. So if this was the free body diagram, this thing would have no acceleration right now, because weight cancels out with normal force. And we know we need the acceleration to point to the left because the car is moving with the apples. So acceleration has to point left. For that reason, friction force must point left. So friction points left. We know this because the truck is slowing down. Another way of thinking about it, which way do the apples want to go? Think about it when you're in the car and someone slams on the brake. you jolt forward, right? So what stops us is friction from jolting forward, basically. It moves in the opposite direction. So that's that answer. And then the only thing left is we need to find the maximum speed of the truck. This is probably going to be the most math-intensive problem of the day. Very complicated, a lot of variables. You will hate it, and I will like it. And that's what we're going to do. So, honestly, this is two parts. One part is kinematics, because we're talking about the velocity. I gave you a distance, 20 meters. We're definitely talking about kinematics. We're also talking about forces, obviously, as well. So it doesn't matter which one you start with. You can either start with forces or velocity and kinematics. I'll start us off with forces. I just drew the free body diagram already, so step 1's done. Step 1.5, there's no components. We're good. Skip that. Next, I have F net x equals the forces to the right, none of them, minus the forces to the left, Fs. And I set that equal to mass times acceleration. Now right now I got to solve for that acceleration. And the reason why is because the acceleration there is the same acceleration that shows up for kinematics. So we'll be good. So that means I need to find out what Fs is. Now here's the thing. Fs, static friction force, that is going to be the max static friction force. Why? Because I said, what is the maximum speed? If I want the maximum speed, I need the maximum friction, don't I? So then that means negative, and then friction is mu s times the normal force equals ma, because friction's mu s times the normal force. Mu s I gave us, it was 0.3. And the normal force, I don't know exactly, but I know it has to be mg because the y forces cancel each other out, giving us an acceleration of 0 in the y. So then that equals ma. You'll notice that even though I don't know the apples, the mass of the apples, it doesn't matter because mass cancels. Whenever they don't give you something in physics, it means it cancels. That happens a lot with friction. So the acceleration must be negative 0.3 times 9.8. And that will be an acceleration of negative 2.94 meters per second squared. So we're done the forces part. And now the only thing left is we need to find the kinematics part. So for the kinematics part, I write V initial, V final, acceleration, time, and displacement. V initial is what I'm solving for. I wanted the max speed. V final is 0 because we're coming to a stop. The acceleration we just found, it's negative 2.94. We don't know the time, and delta x, it said it came to a stop in 20 meters. So then that means we can calculate for VI using the equation that does not have time in it, which is the squared one. V final squared equals V initial squared plus 2a delta x. That means 0 squared equals V initial squared plus 2 times negative 2.94 times 20. That's going to simplify to 0 equals VI squared minus 117.6. I add 117.6 to both sides, and then I take the square root. So V initial is going to be 10.8 meters per second. And that's going to do it for that problem. And basically it. So that's basically the end of the review. Are there any questions on that last one?
Did you not split it into the x and y axis just because the motion is only...
Yeah, 1D motion, exactly. No y motion. Any other questions? Okay, great. Now this then brings us to the conclusion, which means I'll say the final note that I want to say. And this actually does not have to do with the exam, but my exam review. You should be wondering, why on earth is some guy who, obviously charges for money normally when he meets for his tutoring lessons, why did he just put together this 3-hour-long review for nothing? And you could make the argument that, it's part of it's to get more clients later on, and I'll probably charge for the next exam review, and all of that's probably true. But that doesn't explain why, this was a massive amount of work on my end. I'm not going to get the money back. I can pretty much guarantee you that. But I didn't do it for the money. I did it because I want to become the greatest tutor of all time, and that's my goal. And I hope that I was able to instill that in you, at least with the questions we did today. So if you do have any more questions after this review, please let me know. Email me, text me. If you do know anyone who's looking for a tutor, or even just tell them, share this exam review with anyone in your class or whatever, please do that too. And I would appreciate that. So with that, have a great rest of your day, and best of luck on your exam. Bye-bye.